John Carney, I'm from Excite Labs, and I'm going to talk about how we were able to achieve the Dash uh, data plane performance at 800 gig using DPDK. And so what I'll do first is I'll talk a little bit about what is SONiC Dash. I'm sure I know some of the people here know what it is, but I think I'll review that. And for people who don't know what it is, I'll explain that. And then I'll explain how we implemented Dash in DPDK. And then I'll go through some of our 800 gig performance results for Dash. So what is SONiC Dash? So SONiC Dash is a Linux Foundation project started in October of 2021 by Microsoft. It stands for Disaggregated APIs for SONiC hosts. And what it does is it defines the stateful host networking services that are the services that the hosts use in the cloud. It enables a broad set of technology providers to create performance, power, cost optimized implementations. So if you think about the history of the services that are run in the cloud, they've used data planes such as OVS or VFP. These are sort of primitive operations, and the SDN controllers can link together those primitive operations to create services. But over the decade and a half of using those data planes, what's emerged is really a set of well-known, well-defined services where we can now define the services and the APIs, and we can really optimize the performance of those. So instead of building the service on top of these primitives, we're defining them in a way where implementations of those APIs can be optimized, especially by using DPUs. And the idea is really to extend the success that SONiC has had for the stateless networking features or services in the cloud to the stateful features that the hosts use in the cloud. Here's an example of Dash on a smart switch. So first I'll say that the Dash data plane and Dash could actually run in many different places. It could run on the host itself. It can run on the NIC in the host. It could run on an appliance. It could run in a smart switch. And there's some particular value when it's actually not running on the host. Talk about that a bit. So in this diagram above, you have your servers. Those servers have CPUs and NICs. Typically, that server may be a bare metal server where there's just a single tenant. That tenant needs to be isolated from the cloud infrastructure. That server may be running VMs. There may be multiple tenants sharing those VMs on that server. And typically, it's the NIC where the SDN policy is applied, where there's security, isolation, billing, those kinds of features are running on the NIC. But what that requires is that NIC be capable of handling those services at the performance and scale required by the workloads that are running on that server. And there are workloads that may exceed the capabilities of that NIC. For example, very network intensive, very high connection rate kind of workloads, like sort of network function kind of workloads. And so that NIC might not be sufficient to be able to handle the SDN policy and enforcement for those workloads. So the idea is that you could run a data plane disaggregated from the server on a DPU, for example, in the smart switch. And in that case, traffic would be tunneled. So if you look at the server on the right and the VM on the right, traffic would be tunneled through the NIC to that DPU, and all the host services would actually be implemented for that VM on the DPU rather than being implemented or executing in the NIC. And you can have a mix. You could say some VMs that have modest workloads, their services are being applied on the NIC. Other VMs that have very high high connection rates can be run on the DPU. The other benefit of this is that you could develop new services that may not be implementable on the NIC. It may be some legacy servers and NICs, and if you develop new services, those can be developed on the DPU, and they can be offered to the tenants that are running on those servers and on those VMs. So we'll take a look at one of the services of Dash. There's about 7 services defined for Dash, but sort of the most basic service and the one from which all of the others sort of extend is called the VNet to VNet service. And so for the VNet to VNet service, the data plane has to apply several lookups and transformations on the packets. They have to map the overlay network of the tenant to the provider's underlay network. The Dash data plane has to do stateful connection tracking for both TCP and UDP connections. There's a requirement that Dash perform 5 access control list operations per connection setup. Data plane has to also do accounting for billing. It also enforces bandwidth, packet rate, and flow scale limits. And one of the very important things that the Dash data plane has to do is it has to synchronize state from one instance of a Dash data plane to another instance of a Dash data plane for the purpose of high availability. So that if a link goes down, if a DPU fails, that from the tenant perspective, there's no loss of connectivity. All of their connections in the network will stay up and continue to run. And now if you take a look at what a Dash data plane has to do at 800 gig performance level, there's very high scale requirements. It has to support 12.8 million outbound routes in the route table, 128 million ACL prefixes, 32 million mappings, and perhaps the heaviest requirement of the scale is that it has to support a connection table with 128 million active flows in it. This is enormous scale. This scale of these databases requires many tens of gigabytes of DRAM. And that's challenging for any kind of Dash implementation because what it means is that really in order to process packets in the Dash data plane, it just requires many, many accesses to DRAM. There's no ability to rely on caches or locality for performance. And in fact, we'll talk a little bit later about the testing. And the testing specifically is done in a way to make sure that any implementation of Dash can handle this scale, assuming that there's no locality. This is a look at a diagram of the Excite Labs Dash DPDK software architecture. So the gray boxes are hardware, and the blue boxes are cores. In our case, they're ARM cores. If you look at the hardware on the bottom, there's the NIC, or in the case of our DPU, we call it the E unit. Really doesn't matter. What matters is that the hardware provide a POLMO driver, a DPDK POLMO driver for interfacing to the Ethernet, the network. And then on the top is the memory system. And the memory system is where the databases live, where the flow tables live, your counters, rate limiters, packet buffering. And then the software is in the middle. So in our architecture, there's a control core that's responsible for initialization, for some periodic sort of things like stats collection. And then there's the gRPC server, and this is where configuration from SONiC or from the libsci comes into the data plane. And then there's a series of cores, worker cores, and this is where the main packet processing happens in the Dash data plane. And then that's scalable to as many worker cores as you can put. And then there are aging cores, and the aging cores are really doing some background processing where they're looking at this connection table, and they're deciding whether flows have been idle for an excessively long amount of time, and they're basically recovering the resources of that connection table for flows that may have gone idle. Perhaps the endpoint power was disabled, something happened at an endpoint, and you have to eventually recover those resources from the flow table. And in our architecture, aging is also something that's scalable. You can apply multiple CPUs to this aging process. Some key attributes of the Excite Dash architecture is that it's platform independent. So we didn't implement this Dash data plane to only run on an Excite DPU. We implemented it as a platform independent application. We've run it on x86 servers. We've run it on ARM servers. Of course, we run it on our DPU. Another attribute is that it has linear performance scaling. If you can put N cores on the application, you get a certain level of performance. If you put 2 N cores, you'll get double the performance. And finally, this is a very simple programming model, and I'll talk about that a little bit more. But the idea that we had was that we wanted to keep the DPU programming, specifically our Dash data plane. We wanted to architect it as something that was very simple programming model. If you were to look at the code, it would make sense. It would be understandable. So a little bit more about the programming model. So we make use of the hardware's receive side scaling logic. So the RSS basically performs a static hash over the inner 5 tuple. This allows us to finely balance the overlay flows to CPU cores by looking at the inner 5 tuple. All packets in a flow are processed by the same worker core, so the RSS is essentially pinning flows to cores. And it's a simple run-to-completion processing architecture with proto-threads. So what does that mean? So in software data planes, there's lots of different architectures, different ways of batching and pipelining and doing different things. But the run-to-completion programming model is really the simplest. It's a way of thinking about you receive a packet, you do linear processing on that packet all the way to the completion of that packet. Now, with such high-scale databases, if you were to use a run-to-completion programming model, what will happen is typically you'll stall on your DRAM accesses. As you go to do a route lookup or you go to look in the flow table, any kind of memory access will stall because it's not in the cache. And so we employed something called proto-threads. I think that this is kind of unique in that we took something that really wasn't designed for data plane programming, and we applied it to data plane programming. But it's a very lightweight threading infrastructure that's stackless. And what it allows us to do is at the point in the code where you may stall on a memory access, we can issue a prefetch instruction, and then we can yield. And that will then allow another proto-thread to continue processing. And the other proto-thread itself had yielded on a memory access, and by the time that proto-thread is able to run, that latency to memory has already been hidden by the other proto-threads running their logic. What we found with using proto-threads is that we can maintain this very simple programming model, and it doubled our performance. Then we also have aging cores, and the aging cores are continuously walking the flow table, and they determine if the flows have exceeded their configured idle time. Now, one of the important attributes of Dash is that if you set an aging time on a flow, you want it to age out, if it's been idle for that amount of time with some, amount of accuracy. So for our implementation, if a flow has an age out time of say 30 seconds, we'll always age that flow out within 200 milliseconds. There's a sort of 200 milliseconds of uncertainty around that 30 seconds of when the flow will be aged out, and that's not that easy to do. I've talked about memory latency, memory performance quite a bit, and for a DPU or for any kind of other kind of CPU architecture, this can really be what limits the performance of the application. And so DRAM throughput, latency are limiting factors. The more DRAM access capacity the platform has, the better you'll be able to perform well for the Dash data plane. It's critical that the data structures that are used for the Dash data plane be specifically designed and optimized for Dash. If you don't do this, then you may do a lot more memory accesses than are really required for the data plane. I'll give you a couple of examples of this. Dash requires 5 ACL operations per connection setup. You could imagine some generic ACL algorithm and you just call it 5 times. That may not be optimal. It may be more optimal if you exploit the fact that it's 5 ACLs that use the same 5 tuple. Start to think about how you might be able to optimize your ACL algorithm for being able to do multiple searches with the same 5 tuple. Also, the scale of the rules. And you can think about how to optimize your algorithm around the very specific scale requirements of Dash. Another example of this is in the flow table itself. The flow table is actually what dominates the memory footprint of this application. And if in the aging process you have to visit all of these flow entries, that's a huge amount of memory bandwidth to visit all of the flow entries in the flow table. So again, if you design your data structure specifically for Dash, you could take the information in the flow entries that's critical for aging, and you could separate it out from the rest of the flow table entry. And so now, for example, if that critical information is 1 byte, you could read like a 64-byte cache line from memory and be able to get the aging information for 64 entries at a time, and you drastically reduce the amount of memory accesses that you have to do, for example, for aging. So I think the key takeaway here is that you can't get to the highest performance for Dash without actually designing the algorithms and the data structures to be very specific for Dash. And then finally, in the design of those data structures, if you can minimize the memory footprint, you can actually reduce the system cost. So for example, most Dash data planes would require somewhere between 32 and 64 gigabytes of memory for 200 gig worth of scale, and we can do 800 gig worth of scale within 64 gigabytes of memory, and that's because we're able to optimize the size of those data structures specifically for Dash. So I'm going to, final slide here is I'm going to talk about our test performance, and there's something in Dash, there's a definition of a test called a hero test in Dash. It's really designed to be a stress test. It's really designed to have lots of packet traffic from different flows, again, so that you can't rely on any kind of cache locality. And so the test requires that you have background traffic for 64 million UDP flows, connections. And then you have 60 million TCP background flows. And while that background traffic is running, you have to start and terminate new connections at 12 million connections per second. Not only do you have to do 12 million connections per second, you have to run at 12 million connections per second for 100 seconds without dropping a single packet. And that's challenging because any kind of instantaneous load could make you drop one packet. So over the course of 100 seconds and many billions of packets, might not be that too hard to drop a packet, but this test requires that you have 0 drops. And so when we took our Dash data plane to our testing partner, an independent testing partner, they ran the hero test setup using the Ixia CloudStorm traffic generators. And then on the right, we had what's our DPU evaluation platform with the Excite DPU. Let me just say one thing about the Excite DPU. The Excite DPU, you could think of it as a very energy optimized server SoC with integrated networking and accelerators. So it's a very software-oriented DPU. It has 64 ARM Neoverse N2 cores, and that's the chip that was in the platform on the box on the right. And when this was tested, we ran it with 52 worker cores, 2 agent cores, and 1 control core. And we actually achieved 14.3 million connections per second, exceeding the requirement by 19%. And we did that, again, without dropping a single packet. That leaves some remaining cores for running the SONiC control plane, or you can do anything else with those remaining cores. And in addition to this, we've spent some time looking at this data plane, and we believe that we can achieve an additional 25 to 40% improvement with further optimizations. So with that, I can take questions. Christina. Yeah. So I'll summarize what Christina just said. Christina basically said that there's a real business case behind this technology that what would have taken maybe many VMs in order to get the connection scale can now be done with a single VM because that SDN data plane is now capable of handling the workload that was really running on that VM. So instead of the workload being limited by the SDN data path, now the SDN data path is really scaled up so that the workload can run on a single VM. Is that? Right. What's the ratio of NIC to Dash, and how many NICs can a single Dash? So, I think that, the typical use case of Dash is in a smart switch. And like the number of links or the number of ports like connected to the switch, I think can really be flexible. I mean, in the case of the E1, like we support 2 by 400 gig E. So in a smart switch, you'd have two 400 gig links to the switch. But the fact is, you could be 8 by 100. It doesn't really matter because the traffic gets balanced across those links and then gets processed by the dash data plane.
Yeah. So we can talk all day about prefetching and cache lines, and I've been doing this for a long time as well. My real question then is, what does it mean for OPI? Similar to like 2 presentations ago, that question was raised as well. Are you saying we should do this, like we should expose Dash, or what is the real message for OPI specifically, right?
Yeah, I mean, I think one thing is to just one sort of overarching thing is just here's another workload, and it's a workload that's of interest to cloud providers. It may be of interest to enterprises eventually. These services are services potentially that all hosts need, and yeah, how do you roll this out in a way where an enterprise type customer could run this on either DPUs, right? Host attached, or maybe, there may be more discussion in OPI about other instances of DPUs, like DPUs that are, switch attached instead of host attached. Because I think that there's a much broader set of use cases for DPUs than just DPUs that are directly attached to the host.
Thanks a lot, Sean. Really appreciate it.